Hello and welcome to Earthly Teachings, where learning is clear and powerful. Today we are working on Mathematics N6, and we'll be tackling Module 5, Volumes of Revolution. Let's learn together. In this video, we'll learn how to calculate the volume of a three-dimensional solid created by rotating a two-dimensional area around an axis. We'll cover two main methods for calculating these volumes, the disk washer method and the cylindrical shells method. Let's get started with our first set of problems. Our first problem asks us to calculate the volume generated when the area under the graph of y equals the square root of x, from x equals 1 to x equals 4, rotates about the y-axis and the x-axis. Let's begin by visualizing the area we're working with. This is always a crucial first step. We'll sketch a graph of the function y equals the square root of x, from x equals 1 to x equals 4. The area we are interested in is bounded by this curve, the x-axis, and the vertical lines x equals 1 and x equals 4. First, let's tackle part 1.1, rotating about the y-axis. For rotation about the y-axis, we need to express our function in terms of y. That means we need to isolate x. We start with y equals the square root of x. Squaring both sides, we get x equals y squared. This is the function we'll use for our integration. Next, we must find the new limits of integration in terms of y. We do this by substituting our original x limits into the original function. For the lower limit, when x equals 1, y equals the square root of 1, which is 1. For the upper limit, when x equals 4, y equals the square root of 4, which is 2. So our new integration range is from y equals 1 to y equals 2. Now, which method should we use? This is a key decision. The area is bounded by the curve, the x-axis, and vertical lines. We are rotating it about the y-axis. Notice that our axis of rotation, the y-axis, is perpendicular to the strips we are considering, which would normally be parallel to the y-axis. This suggests the disk or washer method. However, let's consider the strip method specified in the question. The question doesn't explicitly state a method for this part, so we can choose. Let's use the shell method. It often simplifies y-axis rotations of x functions. Let's first attempt the washer method, which involves setting up an integral in terms of y. The formula for the washer method rotated about the y-axis is v equals pi times the integral from c to d of r squared minus r squared, dE. Here, r is the outer radius and r is the inner radius. Looking at our graph, the outer radius, r, is the x value of the furthest vertical line, which is x equals 4. The inner radius, r, is the x value on the curve, which is x equals y squared. Our limits are c equals 1 and d equals 2. Plugging these into our formula gives v equals pi times the integral from 1 to 2 of 4 squared minus y squared squared dy. This simplifies to pi times the integral from 1 to 2 of 16 minus y to the 4th I. This looks like a straightforward integral to solve. Now let's complete the calculation using the washer method. The integral of 16 with respect to y is 16y, and the integral of negative y to the 4th is negative y to the 5th over 5. We evaluate this from 1 to 2. Substituting our limits of integration gives us pi times the quantity 16 times 2 minus 2 to the 5th over 5, minus the quantity 16 times 1 minus 1 to the 5th over 5. This simplifies to pi times 32 minus 32 over 5, minus 16 plus 1 over 5. Combining the fractions, we get p times 16 minus 31 over 5. We find a common denominator, which is 5. So we have 80 over 5 minus 31 over 5, which equals 49 pi over 5. Converting this to a decimal and rounding to 3 places. 49. Py divided by the 5 is approximately 30.788. Therefore, the volume is 30.788 cubic units. Let's quickly check this using the shell method to see if we get the same result. This is a great exam strategy for confirming your answer. The formula for the shell method rotated about the y-axis is v equals 2 pi times the integral from a to b of x times f of x dx. In our case, a is 1, b is 4, and f of x is the square root of x. This simplifies to 2 pi times the integral from 1 to 4 of x to the 3 over 2, d. The integral is 2 over 5 times x to the 5 over 2. Evaluating from 1 to 4 gives the same result, 49 pi over 5. Wait, what happened? We got a different answer. This highlights a common trap. The shell method works by summing up volumes of cylindrical shells. For a revolution around the y-axis, the radius of the shell is x, and its height is fx. However, our area is bounded by the line x as 4, not the y-axis. The shell formula assumes the area touches the axis of revolution. This is where the washer method is superior for this specific setup. So our answer from the washer method, 3788 cubic units, is the correct one. Always draw your diagram to be sure. Now let's move on to part 1.2, rotating the same area about the x-axis. We are still working with the area under y equals the square root of x, from x equals 1 to x equals 4, but this time we are rotating it about the x-axis. Again, let's visualize. The area is rotating about the line y equals 0. Since the area is being rotated about the x-axis, and it touches the x-axis across the entire interval, we can use the disk method. The strip we'll use is perpendicular to the x-axis. The formula for the disk method rotated about the x-axis is v equals pi times the integral from a to b of y squared dx. Our limits a and b are our x values 1 and 4, and y is the square root of x. So we have v equals pi times the integral from 1 to 4 of square root of x squared ds. This simplifies to v equals pi times the integral from 1 to 4 of x dx. Now let's solve this integral. V equals pi times the integral from 1 to 4 of x dx. The integral of x is x squared over 2. So we have v equals pi times x squared over 2 evaluated from 1 to 4. Now we substitute our limits of integration. This gives us pi times 4 squared over 2 minus 1 squared over 2, which is pi times 16 over 2 minus 1 over 2. This simplifies to pi times 15 over 2, or 15 pi over 2, converting this to a decimal and rounding to 3 places. 15 pi divided by 2 is approximately 23.562. The volume is 23.562 cubic units. Now, let's consider a common mistake here. What if we tried the shell method? The problem asks for the volume using a strip perpendicular to the x-axis, which is the setup for the disk method, but a common mistake would be to misapply the shell method. The formula for the shell method rotated about the x-axis is v equals 2 pi times the integral from c to d of y times x di. To use this, we would need to integrate with respect to y, meaning our limits would be 1 and 2, and x would be y squared. In this case, the shell method actually gives the exact same result. Why? Because the area being rotated is bounded by the axis of revolution on one side. This is an important distinction. A disk is a special case of a washer, where the inner radius is 0. A shell can also be used if the region's distance from the axis of rotation is simple to describe. Let's move on to question 2. Here we're asked to find the volume of revolution of an area defined by an ellipse. The equation describes an ellipse centered at the origin with a horizontal semi-axis of 3 and a vertical semi-axis of 2. Since we're in the first quadrant, we're dealing with a quarter of this ellipse. Let's sketch it. The area is bounded by this quarter ellipse and the positive x and y axes. We are rotating this area about the y-axis. The problem statement gives us a very important hint. Using a strip perpendicular to the y-axis. This means we are using the washer method, and we will be integrating with respect to y. This is crucial because it dictates our setup. For the washer method, we need to express the outer and inner radii in terms of y. Since we are in the first quadrant and our area is bounded by the y-axis on the left, the inner radius is simply x equals 0, so r of y equals 0. We need to find the outer radius, r of y. This is the x value of the ellipse. Let's solve the ellipse equation for x. Rearranging the equation, we get x squared equals 9 times the quantity 1 minus y squared over 4. Taking the square root, we get x equals 3 times the square root of 1 minus y squared over 4. Now let's determine our y limits. In the first quadrant, y ranges from 0 up to the vertical semi-axis, which is 2. So our integration will be from y equals 0 to y equals 2. We have all the components we need to set up our integral. We've established that the washer method is the correct approach, with rotation about the y-axis, integration with respect to y, and an inner radius of 0. The formula is v equals pi times the integral from c to d of the outer radius squared di. Plugging in our values gives v equals pi times the integral from 0 to 2 of 9 times 1 minus y squared over 4 di. We can factor out the constant 9. This gives us 9 pi times the integral from 0 to 2 of 1 minus y squared over 4 di. Now we integrate. The integral of 1 is y, and the integral of negative y squared over 4 is negative y cubed over 12. We evaluate this expression from 0 to 2. Let's substitute our limits. This is 9 pi times the quantity, 2 minus 2 cubed over 12 minus 2 minus 0 cubed over 12. The second term is just 0. Simplifying the fraction inside the brackets, we have 2 minus 2 over 3, which is 4 over 3. So v equals 9 pi times 4 over 3. This simplifies to 12 pi. As a decimal, the volume is approximately 37.699 cubic units. This is a very common result. The volume of an ellipsoid with semi-axes A, B, and C is 3 pi times ABC. In our case, the semi-axes are 3 and 2. Since we rotated a quarter of the ellipse about the y-axis, we generated a half ellipsoid. The volume would be 1/2 of 3 pi times 3 times 2 times the other semi-axis, which is also 3. This gives 12 pi. The result matches our calculation, building confidence in our answer. Question 3 presents a new challenge, a trigonometric function. We need to calculate the volume when the area under y equals cosecant of x, between x equals pi over 4 and x equals 3 pi over 4, is rotated about the x-axis. Let's start with a sketch of y equals cosecant of x. The graph has vertical asymptotes where sine of x is 0, which is at x equals 0, pi, 2 pi, and so on. In the interval from 0 to pi, the curve forms a U shape opening upwards with a minimum at x equals pi over 2. We are interested in the area between pi over 4 and 3 pi over 4. We will rotate this area around the x-axis. Since we are rotating about the x-axis and the area is bounded by the x-axis, the disk method is appropriate. The formula, as we've seen before, is v equals pi times the integral from a to b of y squared dk. Our function is y equals cosecant of x. We need to identify our limits of integration and the function to square. The limits a and b are given directly, pi over 4 and 3 pi over 4. The function to square is cosecant of x. Remember, cosecant is the reciprocal of sine. This gives us the integral, v equals pi times the integral from pi over 4 to 3 pi over 4 of cosecant squared of x dx. This is a standard integral you should commit to memory. The integral of cosecant squared x is negative cotangent of x. We have v equals pi times the integral from pi over 4 to 3 pi over 4 of cosecant squared of x dx. Integrating gives us negative cotangent of x, evaluated from pi over 4 to 3 pi over 4. Don't forget the negative sign, it's a common oversight. Now we substitute the limits. This is pi times the negative cotangent of 3 pi over 4 minus the negative cotangent of pi over 4. Let's find the values of these cotangents. Remember, cotangent is cosine over sine. At pi over 4, cosine and sine are both positive square root of 2 over 2, so cotangent is 1. At 3 pi over 4, we are in the second quadrant. Sine is positive, but cosine is negative. So cotangent is 1. Substituting these values back into our expression for v, we have pi times negative 1 minus negative 1. This is pi times 1 plus 1, which equals 2 pi. Converting this to a decimal and rounding to 3 places. The volume is approximately 6.283 cubic units. A good strategy for trigonometric integrals is to draw a unit circle to find the values of the functions at the specific angles. Question 4 involves the area between two curves, both of which are functions of y. Let's read the problem carefully. We have two functions. X equals the square root of y plus 1 and x equals the square root of y minus 1. Both define x in terms of y. This immediately tells us we'll be integrating with respect to y. Let's sketch these. X equals the square root of y plus 1 is a parabola opening to the right, shifted left by 1. X equals the square root of y. Minus 1 is a parabola opening to the right, shifted right by 1. The area is bounded by these curves between y equals 1 and y equals 2. We are rotating this area around the y-axis. Because we are rotating an area between two curves, we must use the washer method. The axis of rotation is the y-axis, and we are integrating with respect to y, so the strip we are conceptually using is perpendicular to the y-axis. The formula for the washer method for y-axis rotation is v equals pi times the integral from c to d of r squared minus r squared. di here, r is the outer function and r is the inner function. Looking at our sketch, x equals the square root of y plus 1 is further from the y-axis. So our outer radius r is the square root of y plus 1, and our inner radius r is the square root of y minus 1. The limits of integration c and d are given as 1 and 2. Now we can set up the integral. V equals pa times the integral from 1 to 2 of the quantity, square root of y plus 1, squared, minus square root of y minus 1, squared dy. Let's simplify and solve this integral. The square and square root cancel out for both terms. This simplifies our integrand to y plus 1 minus y minus 1. Be careful with the negative sign. Distributing it gives y plus 1 minus y plus 1. The y terms cancel out, leaving us with just 2, so the integral becomes v equals pi times the integral from 1 to 2 of 2d. The integral of 2 with respect to y is 2y, so we have pi times 2y, evaluated from 1 to 2, substituting the limits. V equals pi times 2 times 2 minus 2 times 18. This gives us pi times 4 minus 2, which is 2 pi. In decimal form, the volume is approximately 6.283 cubic units. This problem reinforces the importance of identifying the correct method and carefully handling the algebra. Question 5 gives us an area defined by y equals x squared, the x-axis, and the line x equals 1. We're asked to find the volume generated by rotating this area about the x-axis, using a strip perpendicular to the x-axis and then a strip parallel to the x-axis. This question is a fantastic demonstration of how two different methods, disk and shell, can be applied to the same problem. This is a critical skill for N6 students. First, let's sketch the area. It's the region bounded by the parabola y equals x squared, the line y equals 0, the x-axis, and the vertical line x equals 1. The intersection points are at 0, 0 and 1, 1. We will be rotating this area around the x-axis. Let's first tackle part 5.1, using a strip perpendicular to the x-axis. A strip perpendicular to the x-axis means we are integrating with respect to x. Since the area touches the axis of revolution, the x-axis, we should use the disk method. This method is the most natural fit here. So for part 5.1, we use the disk method. The formula is v equals pi times the integral from a to b of y squared dx. Our function is y equals x squared, and the limits are from x equals c to x equals 1. Substituting these values, we get v equals pi times the integral from 0 to 1 of x squared squared dx. This simplifies to v equals pi times the integral from 0 to 1 of x to the 4th dx. The integral of x to the 4th is x to the 5th over 5. So we have pi times x to the 5th over 5 evaluated from 0 to 1. Plugging in the limits, v equals pi times 1 to the 5th over 5 minus 0 to the 5th over 5. This gives us pi over 5. The volume is approximately 0.628 cubic units. This was a straightforward application of the disk method. Now let's tackle part 5.2, using a strip parallel to the x-axis. A strip parallel to the x-axis means we must integrate with respect to y. For this, we must use the shell method. The shell method formula for rotation about the x-axis is v equals 2 pi times the integral from c to d of y times xd. This is a crucial formula to remember. First, we need to express our function in terms of y. From y equals x squared, we get x equals the square root of y for the first quadrant. Next, we need the limits of integration for y. The area is bounded by y equals x squared and the line x equals 1. When x equals 1, y equals 1, so y ranges from 0 to 1. Our limits are c equals 0 and d equals 1. We have everything needed to set up the shell integral. V equals 2 pi times the integral from 0 to 1 of y times the square root of y di. This simplifies to 2 pi times the integral from 0 to 1 of y to the 3 over 2 di. The integral of y to the 3 over 2 is 2 over 5 times y to the 5 over 2. So we have 2 pi times this expression, evaluated from 0 to 1. Substituting the limits. V equals 2 pi times the quantity, 2 over phi times 1 to the 5 over 2 minus 2 over phi times 0 to the 5 over 2. This gives us 2 pi times 2 over 5, which is 4 pi over 5. As a decimal, the volume is approximately 2.5113 cubic units. Notice this is a completely different answer from the disk method. Why? Because the shell method, by its very nature, is calculating a different shape. When you rotate a strip of area, you create a thin 3D object. The disk and washer methods create disks, which are like thin cylinders. The shell method creates shells, which are like hollow cylinders. The disk method correctly calculated the volume of the solid of revolution, which is the volume enclosed by rotating the area Ex2 around the x-axis. The shell method, on the other hand, calculated the volume of the area enclosed by rotating the curve x plus y, the y-axis, and the line YL1 around the x-axis. These are two different areas, generating two different volumes. This is a critical point of confusion for many students. Always draw your diagram to see which area is being revolved. Let's move on to question 6. We are given the function y equals x times 2 minus x. We need to calculate the volume generated when the area between this curve and the x-axis is rotated about the x-axis. Our first step, as always, is to sketch the function. The equation y equals x times 2 minus x represents a parabola. To find where it intersects the x-axis, we set y equal to 0. This gives us x equals 0 and x equals 2. The parabola opens downwards, so the area in question is a dome-like shape. We are rotating this area about the x-axis. Since the area is bounded by the x-axis and is being rotated about the x-axis, we can use the disk method. We will integrate with respect to x. The formula is v equals pi times the integral from a to b of y squared dx. Our function is y equals 2x minus x squared. We also need our limits of integration. Our limits are where the curve intersects the x-axis, which are from x equals 0 to x equals 2. So a is 0 and b is 2. Now we can set up our integral. V equals p a times the integral from 0 to 2 of the quantity 2x minus x squared dx. This looks like a potentially complicated integral, but the first step is to expand the binomial inside the integral. Let's solve the integral for question 6. First, we expand the integrand. Remember the binomial expansion ab squared is a squared minus 2ab plus b squared. Here a is 2x and b is x squared. Expanding this gives us 4x squared minus 4x cubed plus x to the fourth. Now our integral becomes v equals pi times the integral from 0 to 2 of 4x squared minus 4x cubed plus x to the fourth dx. Next, we integrate term by term. The integral of 4x squared is 4x cubed over 3. The integral of negative 4x cubed is negative 4x to the fourth over 4, which simplifies to negative x to the fourth. And the integral of x to the fourth is x to the fifth over 5. We evaluate this from 0 to 2. Now we substitute the limits of integration. This is an exam-style question where careful calculation is key. We have v equals pi times the quantity, 4 times 2 cubed over 3 minus 2 to the fourth plus 2 to the fifth over 5 minus 0. The lower limit evaluates to 0, which is a nice simplification. This simplifies to pi times 32 over 3 minus 16 plus 32 over 5. To combine these, we need a common denominator, which is 15. This gives us V equals pt times the quantity 160 over 15 minus 240 over 15 plus 96 over 15. The sum is 16 over 15, so the final volume is 16 pi over 15. In decimal form, this is approximately 3.351 cubic units. A helpful tip for checking, though not a proof, is that the volume of a sphere of radius r is 43 pi r cubed. This parabolic shape is somewhat similar, so a result of 1615 pi, which is 1.06 repeating pi, feels plausible. Question 7 asks for the volume generated by rotating the area bounded by y equals e to the x over 2, the x-axis, the y-axis, and the line x equals 2, about the x-axis and the y-axis. Let's first visualize the area. The curve y equals e to the x over 2 is an exponential growth function. The other boundaries are the x-axis, y at 0, the y-axis, x at 0, and the vertical line x at 2. This forms a region in the first quadrant. For part 7.1, we rotate this area about the x-axis. Because the area is bounded by the x-axis, we use the disk method. We will integrate with respect to x from 0 to 2. The formula is v equals pi times the integral from a to b of y squared d. Substituting our function and limits, we get v equals pi times the integral from 0 to 2 of e to the x over 2, squared at. Using the exponent rule, e to the a to the b is e to the ab. This simplifies to v equals pi times the integral from 0 to 2 of e to the x dx. The integral of e to the x is just e to the x. So we have pi times e to the x evaluated from 0 to 2. Substituting the limits, we get pi times e to the 2 minus e to the 0. Since e to the 0 is 1, the volume is pi times e squared minus 1. As a decimal, the volume is approximately 20.086 cubic units. Make sure you remember that e to the 0 is 1, not 0. Now let's do part 7.2, rotating the same area about the y-axis. For y-axis rotation, the shell method is often the most efficient for functions of x. We will integrate with respect to x from 0 to 2. The formula for the shell method about the y-axis is v equals 2 pi times the integral from a to b of x times f of x dx. In our case, a is 0, b is 2, and f of x is e to the x over 2. This gives us v equals 2 pi times the integral from 0 to 2 of x times e to the x over 2 d. This integral requires a special technique called integration by parts. The formula for integration by parts is the integral of u dv equals uv minus the integral of v du. We must carefully choose our u and dv. A good rule of thumb is LIATE: logarithmic, inverse trigonometric, algebraic, trigonometric, exponential. We have an algebraic term, x, and an exponential term, e to the x over 2. A comes before e, so we choose u equals x. If u equals x, then its derivative du is dx. If dv equals e to the x over 2 dx, then v is 2 times e to the x over 2. Now we can apply the formula. The integral of x e to the x over 2 is 2x e to the x over 2 minus the integral of 2e to the x over 2 dx. This simplifies to 2x e to the x over 2 minus 4e to the x over 2. This is the indefinite integral. We now need to evaluate it over our limits of 0 to 2, and don't forget to multiply by 2 pi. V equals 2 pi times the quantity, 2e to the x over 2 minus 4e to the x over 2, evaluated from 0 to 2. This will require careful substitution. V equals 2 pi times the quantity, 8e minus 4e, minus negative 4e to the 0. This simplifies to 2 pi times 4e plus 4. As a decimal, the volume is approximately 25.133 cubic units. This question was a great way to practice integration by parts within the context of volumes of revolution. Always remember the Liat rule to choose u and dv. We have reached our final question, number 8. This is another classic two-curve rotation problem. We need to calculate the volume generated by rotating the area bounded by the ellipse x squared over 9 plus y squared over 4 equals 1, and the line x over 3 plus y over 2 equals 1 about the x-axis. The problem specifies to use a strip perpendicular to the x-axis. Let's begin with our sketches. We need to see the bounded area. The first equation is our ellipse from question 2, with semi-axes 3 and 2. The second equation is a line. The easiest way to sketch it is with its intercepts. When x is 0, 0, y is 2. When y is 0, x is 3, is 0, x. So the line intersects the ellipse at 2 points. We can find these points by substitution. Substituting this into the ellipse equation and simplifying shows that the intersection points are 3,000 and 0, 2. The area bounded by the ellipse and the line is the region between them. We will rotate this area about the x-axis. The problem specifies to use a strip perpendicular to the x-axis. This is a setup for the washer method. The formula is v equals pi times the integral from a to b of outer radius squared minus inner radius squared dx. Let's identify our components. The outer curve is the ellipse, so r of x is the upper part of the ellipse. The inner curve is the line, so r of x is the line itself. The limits of integration from our sketch and intersection points are from x equals 0 to x equals 3. We have determined our outer and inner radii and our limits of integration. Now we set up the integral for question 8. V equals pi times the integral from 0 to 3 of r of x squared minus r of x squared dx. This is our integral setup. Let's simplify the integrand before integrating. This is the most crucial step for avoiding mistakes. Expanding the first term gives 4 minus 4x squared over 9. Expanding the second term gives 4 times 1 minus 2x over 3 plus x squared over 9, which is 4 minus 8x over 3 plus 4x squared over 9. Now we subtract the inner term from the outer term. The integrand simplifies to negative 8x squared over 9 plus 8x over 3. Notice the 4's cancel out. So our simplified integral is v equals pi times the integral from 0 to 3 of negative 8x squared over 9 plus 8x over 3 dx. This is much easier to integrate. Now we integrate term by term. The integral is pi times negative 8x cubed over 27 plus 4x squared over 3, evaluated from 0 to 3, substituting the limits. V equals pi times the quantity, negative 8 times 3 cubed over 27 plus 4 times 3 squared over 3, minus 0. This simplifies to pi times and negative 8 plus 12. Which is 4 pi. The volume is approximately 12.566 cubic units. This question perfectly combines several key concepts: sketching, identifying the correct method, washer, algebraic simplification, and integration. Let's quickly review the common pitfalls we've seen today and some strategies to avoid them. The first and most important strategy is always to draw a clear labeled diagram. This will help you identify the correct method. Mistake number 1 is confusing the disk washer method with the shell method. Remember, disk washer involves revolving a strip perpendicular to the axis of revolution. Shell involves revolving a strip parallel to the axis of revolution. Another common mistake is incorrect integration limits. Always make sure your limits correspond to the variable you are integrating with respect to. Algebraic errors, especially with expanding and subtracting in the washer method, are very common. Take your time with these steps. And finally, don't forget the negative signs and the constant pi in your final answers. Thank you for joining Earthly Teachings today as we worked through this activity on Volumes of Revolution for Mathematics N6. We covered the disk washer method and the shell method, applying them to various functions, including algebraic, trigonometric, and exponential curves. I hope this step-by-step tutorial has been clear and helpful. If you found this video useful, please like it, subscribe to Earthly Teachings for more math content, and keep learning with us. See you next time.